everyone. In today's video, we're going to cover linear versus nonlinear functions. Our learning target for today is I can determine if a function is linear or nonlinear. First, looking at linear functions, we have three ways to determine if a function is linear or not: through graphs, through equations, and through tables. Now, a linear function will be a function that will make a straight line when it's graphed. An equation is linear if it can be written in the form y equals mx plus b, where m is your slope and b is your y-intercept. And then a table is linear if it shows a constant rate of change throughout the entire table. Now looking at our examples, we'll use functions to fill out a table of values and create a graph. And then we'll look for any patterns among the functions that are linear and those that are not. So looking at number 1, we have y equals x squared plus 1. That's our function. We have a table of values with x values of -2, -1, 0, 1, and 2, because we want to plug in a varied amount of x values, some negative, some positive, to get a good representation of what our graph would look like. And then we have our graph. So first, if we plug in -2 into x and y equals x squared plus 1, we'd have the equation -2 squared plus 1. -2 squared is -2 times -2, which is 4, plus 1, which would give me a y value of 5. So if x is -2, I have a y value of 5, so I can plot that point here. Now if x is -1, I'd have -1 squared, which is -1 times -1, plus 1, which will give me a value of 2. So then if x is -1, I'd have a y value of 2, so I can plot that point. If x is 0, 0 squared is 0, plus 1 is 1, so a 0, 1. 1 squared is 1, plus 1 is 2, and then 2 squared is 4, plus 1 is 5. So I'd have 1, 2, and then 2, 5. So here I can see that this graph would look something like this. This is called a parabola. Any x squared is a parabola graph. This function is not linear because it's curved. No, not linear. Looking at number 2, we have y equals 1/2 x. So here, again, I have -4, -2, 0, 2, and 4 for my x values. Again, some positive, some negative, to get a good representation of what my graph will look like. 1/2 times -4 would be -2. So at -4x, I would have -2y. -2 times 1/2 would give me -1. So x at -2, I would be at -1. 0 times 1/2 is 0, so I go through the origin 0, 0. 2 times 1/2 is 1, x value 2, I have y value 1, and then 4 times 1/2 is 2, so x value 4, I have 2. If I graph this, I can see that this will make a straight line. So this function is linear because it's a straight line. So when I look at the differences between number 1 and number 2, notice here I have an x squared and no exponent here. So if a function is linear, it's going to be in the form y equals mx plus b, our slope-intercept form. If it's nonlinear, the x will have an exponent, or the x could possibly be in the denominator as well. Now looking at problems 3, 4, and 5, again, we have a function, a graph, and a table. I want to see if the function is linear or not. So number 3, we have y equals x cubed. Again, I have a varied amount of x values, some negative, some positive, to get a good representation of what my graph will look like. So if I have -2, -2 cubed would be -2 times -2 times -2, which is -8. If I plot that point, I have x value of -2, y value of -8. -1 would be -1 times -1 times -1, which is -1, so I'm at -1, 1. 0 cubed is 0. 1 cubed, 1 times 1 times 1, which is 1. And then 2 cubed, 2 times 2 times 2, which is 8. So I'm here at 2, 8. Now if I graph this, this is called a cubic function. So this is nonlinear because it's not a straight line. Again, I have an exponent of 3 here, any exponent with my x values, and it will not be a linear function. Number 4, I have y equals 1.5x plus 2. If I plug in -4, 1.5 times -4 is -6, plus 2 would be -4, so I'd be at -4, -4. -2 times 1.5 is -3, -3 plus 2 is -1, -2, -1. 0 times 1.5 is 0, plus 2 is 2, so 0, 2. And then 2 times 1.5 is 3, plus 2 is 5, so 2, 5. And then 4 times 1.5 is 6, plus 2 is 8, so 4, 8. If I graph this, I can see this is a straight line. This is a linear function because it's in y equals mx plus b form, slope-intercept form, and I can see in my table that this is increasing by a constant rate. For every x value of 2 that I'm increasing by, my y values are increasing by 3 each time. This is constant. Every x value that I'm increasing by has the same amount of y value that I'm increasing by. Now looking at number 5, we have y equals 12 divided by x. So here I'm going to plug in 1, 2, 3, 4, and 6. 12 divided by 1 would give me 12. 12 divided by 2 would give me 6. 12 divided by 3 would give me 4. 12 divided by 4 would give me 3. And 12 divided by 6 would give me 2. Plotting these points, I'd have 1, 12, 2, 6, 3, 4, 4, 3, and 6, 2. Seeing here, this is a curved line. This is an exponential function. This is not linear because, again, it's a curved line. And I can also see in my table, I'm not decreasing or increasing by a constant rate. I'm decreasing here by 6, then by 2, then by 1, then by 1, and it's not a linear function. Now, what differences did we notice about the equations that were linear and those that were not? So the ones that were linear were in slope-intercept form, and then any equation where x was raised to an exponent or was in the denominator was not a linear function. And then what differences did we notice about the tables that were linear and those that were not? So the tables that were linear, those increased by a constant rate of change every single time. And then the tables that were not linear did not increase by constant rate of change every single time. In today's lesson, we learned a linear function is a function that will make a straight line when it's graphed, a function that has y equals mx plus b as its equation, and has a table that shows a constant rate of change. A nonlinear function is a function that will be a curved line when graphed, a function that has an exponent or x in the denominator, and has a table that doesn't have a constant rate of change. That's a wrap on today's video. We'll see you in the next one.